Okay, so let's start with the talk from by Guillermo Barbadillo that will be AI recent, past, and near future. So Guillermo is an AI researcher at Ndea, where he's working on general artificial intelligence. No, Ndea is the startup created by François Cholet, and he's working there since this year. No, before he was working on Veridas. On facial biometrics. And he's also known because he's a Kaggle Grandmaster. So he has competed in many Kaggle competitions and won more than one, no? I think, of them. So he's a very good expert on this. He was also the second prize in the ARC 2024 competition. So he knows very well the competition he will be speaking today about. He's also, he is involved in a podcast, the Tertulia. I recommend you to listen it because it's quite interesting because it mixes like technical knowledge with non so technical knowledge, and it is in Spanish, and they, I think it's a good podcast to listen. So let's welcome Guillermo and how we learn a lot with him.
Okay, can you hear me well? Yes? Okay, so the goal of this talk today is to do a recap of where AI is today and to know what are the limits so you can later solve them and reach AGI. Okay, so that's the goal. So this is the index. First, we are going to answer what is intelligence. Then we are going to review the progress of AI in the previous years. And then we will go into what are the limits of deep learning and how we might achieve AGI. Okay, so what is intelligence? So first, let's say what is not intelligence. For example, playing chess is not intelligence, playing Go is not intelligence, driving a car is not intelligence. Those are skills, okay? This is very important. People usually confuse skills with intelligence, but we have to be aware that skills are not intelligence. In the most extreme case, we can imagine a computer with a lot of memory that is able to store all the positions in chess and what is the optimal next move. And that computer will be totally dumb, but will be able to play chess at the highest maximum level. So please keep in mind that skills are not intelligence. And if we choose a fixed task, we can buy arbitrary levels of skill. We can use unlimited priors, we can use unlimited training data, we can use unlimited compute, and if we have a clear defined problem, we will be able to achieve any level of skill that we want. But this is not intelligence. This is a method to get a skill. So what is intelligence? Intelligence is skill acquisition efficiency. A skill is the product of intelligence. So a very intelligent person will acquire skills faster than other people, needing less data than other people, needing less prior knowledge than other people. That is intelligence. It's the process that transforms experience into skills. Okay, and how we can measure intelligence? First thing is that the test that we are going to use has to be unknown to the tested, okay? This is very important. And we have to control for prior knowledge. For example, how familiar is the person or the system with the task? How many training experience did the system need to achieve the skill? And finally, the generalization capability, okay? And this is how different is the test compared to the training data that you have been given, okay? For example, you have probably seen intelligent tests online, and if you take one of those tests, the result probably will be a good estimation of your intelligence. But if you previously practice doing intelligent tests, the results will not be a good estimation because you have already seen the kind of tests that are used in intelligent tests. And thus, when you take a similar test, you will get higher results than otherwise. So the tests need to be secret and new if you want to measure intelligence. In humans, high skill level is a sign of intelligence because all the humans start more or less from the same point. We were all born babies. We didn't know anything. And if someone is able to reach a high level of skill, that probably indicates that he's very intelligent because other humans had the same opportunities and were not able to reach that level of skill. Okay? That is why we tend to confuse skill with intelligence. Okay? And finally, these artificial intelligence systems, Deep Blue, AlphaGo, or Waymo, they only do one thing. So they show high skill in their area, but they are not able to learn to do other things. So that is not intelligence. They have some intelligence, because intelligence is not white or black, there is a spectrum. But if you can only do one thing, that's not very intelligent. Okay, so being said that, let me present you ARC-AGI 1. Probably you already know about this, but just in case. So ARC-AGI 1 is a test of intelligence, okay? And it is designed with all these ideas that I have already shared. So for example, the test set is private. Only François Solet knows which tasks are on the private set. The prior knowledge needed to do the ARC tasks are fixed and public. So you only need notions of objects, numbers, counting, basic geometry. You don't need any other knowledge to do that kind of test. And finally, the generalization capability is also fixed because for each task, you have some training samples, and then you have a test sample. And generalization means that given those training samples, you are able to create a transformation that applies on the test set. If the test set is very different from the training samples, that means that you have high generalization capability. If it is very similar, the generalization capability is lower. Here you have some samples in a bigger format, a very simple task, like you see. You only have to understand that you have to fill the holes with yellow. And here you have other examples, just to give you an idea of how ARC-AGI 1 looks. So it is a test that is designed to measure intelligence. Okay, any questions so far? No? Okay, so let's go to see how AI has progressed in the recent years. So this section has 5 subsections. So first we are going to see how LLMs works. There we are going to go to reasoning models, then agentic models. Then we are going to see what is the fuel behind all this progress. And finally, some improvements that we have seen in the open source ARC-AGI challenge. Okay? So let's go with LLMs. First LLM is not from 2020, but I believe that's the year when GPT-3 was released. So probably that was the first model that was useful for doing things. Okay, what is the training recipe that we have to follow to train an LLM? It is very simple, and probably any of you, given enough resources, could do this because it's a very, very simple recipe. So first, we are going to take a transformer and we are going to train it in all the data from the internet. We take all the data that we can and we train the model to predict the next word. Then we have another phase that is the mid-training, where we keep training the model on higher quality data, okay? Because internet is full of trash. You have many shops that don't really add useful information to the model. So we have another step where we use only high quality data, okay? And this creates a model that is able to predict what is the next word. But this is not a chatbot or an assistant, okay? This is just a model that, given some text, it will be able to keep writing text. So it might be the case that you make a question to the model, and instead of answering, it will create similar questions as yours, okay? So then we have the post-training phase, where we first do supervised fine-tuning. We have some data sets of answers and questions and answers, and that allows the model to start transforming into an assistant. And finally, we have some preference alignment step where we could teach the model to give given two different answers, to give more probability to one, learn also to reject some unsafe question, some kind of that. So as you can see, the recipe is very simple. It's mostly supervised training. In the last step, there could be some reinforcement learning, but not necessary. It's just optional. So the recipe is very simple. The difficulty part is the scale, that these models are trained in clusters with thousands of GPUs, with a lot of data. So the challenge is more an engineering challenge than a conceptual challenge, because as you can see, the recipe is super simple. Okay, what is the problem of LLMs? The problems of LLMs is that they simply imitate how humans write, okay? They are, you can see an LLM as some kind of imitation learning. You have text, and the LLM learns to imitate how we write. And if you have done some experiments with reinforcement learning, and you have also tried imitation learning, for example, if you take an example of a video game, a driving car video game, and you train a policy model on expert trajectories, this car will drive well enough when it is on similar data where it was trained on, but suddenly it will go to another place of the road. There is no data for that part, and the model does not know what to do, so it will crash. And this is very typical. If you try, you can try this on simple environments, and it happens. It has happened to me. So if you only do imitation learning, the models do not learn how to adapt to new situations. They have learned how to act in some situations, but when something unexpected happens, they don't have the intuition to adapt. So this causes that LLMs are only useful when the task that you want to do is already present on its training data. So an LLM will be good for a task based not on difficulty of the task, but on familiarity. You could ask something very difficult, some math problem, for example, and if the LLM has been trained on similar data, it will probably do well. But you could ask something very, very simple, something that is trivial for humans, and if that is not present on the training data, the model will do very bad. So it's not a matter of difficulty, it's a matter of familiarity. The good thing is that internet is so huge that it almost covers anything, but there are always gaps. Okay, and I want to relate this to ARC-AGI, and here you can see a plot where the x-axis is the time, and on the y-axis we have the score on ARC-AGI 1. And you can see that it starts here. I'm not sure what is that number. Probably it's 2018 or 2019 until today. And the progress of LLMs was almost none. We can see at the end that they were making some progress, but still very, very far from humans. And meanwhile, in that time, the size of the models increased by many, many orders of magnitude. Okay, so even scaling the models was not enough to make good progress on ARC-AGI. And that was because ARC-AGI was an intelligent test. It contained new tasks, and the models, the LLMs, did not have too much adaptation capability. So that's why they score poorly here. But at the same time, there was a belief, not by everybody, in the AI research community that scaling was all you need. And I have put here some evidences of it. But you can see in the previous slide that clearly scaling was not enough to solve ARC. Okay. Okay. So then suddenly reasoning models appear at the end of 2024. First good enough reasoning model was O3. I'm not sure if you remember the release of O3. I do remember it. O3 was very, very good at ARC-AGI 1. We are going to see that very soon. The thing is that they did not disclose too many details about how O3 was trained. Even if the company is called OpenAI, they did not publish many details. They did show some interesting scaling laws where you can see that the more you train the model, the better it gets, solving math problems, and also the more test time compute you use, the better the results went. So let me jump to here. I will go back. And here you can see the point where O3 was released. So you can see that the jump is huge and clearly a very different tendency. And these are other reasoning models that were released later. So scaling was not enough. A change of paradigm was needed to solve ARC-AGI. So let's go back. So we have seen that O3 was released, but without many details. We didn't know how it worked. But luckily, 1 or 2 months later, DeepSeek, a Chinese company, published and released R1 with a very, very extensive paper. It's very interesting. I recommend you to read it. And it got very, very good scores in different benchmarks. And the good thing is that since they released the paper, it was very clear that the main difference between LLMs and reasoning models was reinforcement learning. Okay? In addition to these steps that we have seen in the LLM training recipe, they add an extra step, an additional step, where we do reinforcement learning. And how this is done. So there are many ways, but we are going to see briefly how DeepSeek R1 was trained. Okay, so to train with reinforcement learning, in this case, we need pairs of questions and answers, and we need answers that can be verified. For example, mathematical problems are a very good case for this. So, for example, we have here an equation, and we are asking for what is the solution for x. Okay. We take that question, we send it to our LLM, and we sample many answers. You probably know that when using an LLM, we can use a parameter named temperature that allows to generate many responses, and we do that, okay? We generate many responses, and then we score each reward. In this case, we are only using two criteria for scoring the rewards. We are measuring if the response is correct and if the response follows the format. We give more weight to correctness than format, but we use those rewards. But in reality, you could define all the rewards that you want. You can take a small LLM, you can create a small training data set, and you can craft any reward function that you want. You can do this for free on Google Colab or other services. As long as the model is small, you can try this. And there are many Python libraries that allow you to try this easily. Okay, so we score all the different answers, and then we compare the answers between them and use that to compute the loss and update the model. So the method, again, is very simple. Once you know it, it's super simple, and anyone can do it today. Okay. The good thing is that this kind of training makes the model much more robust and teach the model to how to search when you ask something, how to search a question for how to search the answer for your question, and also teaches the model the notion of correctness, because an LLM doesn't know if something is correct or not. You can answer something, the model can give you the correct answer, and if you say the model, this is not correct, try again, the model will do a different thing and will return a different answer. It does not have the notion of correctness. But when we train with reinforcement learning, the model is able to learn that. It's able to learn to search, and is able to know when something is correct. That is what allows to solve difficult problems and spend more time reasoning to give an answer. Okay, so yeah, this was the recipe for LLMs, and we are at a final step, and suddenly we have models that are much better and that have they have some capability of adapting to novelty that LLMs did not have. But on that year, the second version of ARC-AGI, ARC-AGI 2, was released. The format is the same. The only difference is that the tasks are more difficult. So they require a stronger generalization. They require composition of rules, not just simple rules. So it is a more difficult test, although still it is solvable by humans, by normal humans. It was tested on random people. So it is simple for humans, but we could see that even if ARC-AGI 1 was solved, ARC-AGI 2 was not solved, and the progress again was slow. And then we reached to agentic models. Any questions so far? No? Second. So this is very recent. Probably the change was on November of 2025. And suddenly we see again a very fast progress on ARC-AGI 2. And you might have the question, why did this happen? Because I can tell you that the training recipe was still the same, okay? We are using the exact same recipe as our reasoning models, but there was one change. Instead of training just on pairs of questions and answers, they started to use environments. Okay, so this is very important because when you use an environment, an environment can be really anything. It could be a game, it could be a simulation of your computer where you have some code repository. It could be anything. But the good thing of environments is that they allow the models to learn how to use tools. That is very useful for doing software engineering. And they also allow the models to learn to do multi-step solutions. Because previously, we ask the model, okay, this is a mathematical problem, solve it. And the model will think and return an answer. Now, when we train a model with environments, the model could try to use tools, could do some multi-step solutions, could divide the problem into smaller parts and address each part sequentially. So it gives the model like a new access to learn, and this is the reason behind the great progress that we have seen in the past months with agentic tools. Probably you have heard a lot about Cloud Code, Codex, there are many others. And suddenly we have models that are quite good at software engineering and can do many tasks. Okay, and one interesting thing of this cycle of reasoning models is that there is some kind of virtuous cycle, okay? Because you can use your current best model, for example, let's say GPT 5.4, and you can use that model to generate the high quality data that will be used during mid-training, and that results on a more stronger model that will be GPT 5.5. So it's kind of a virtuous cycle because you can use your models to generate better data for training the next generation of models. And this is happening. This is why current models, even many times without reasoning, are able to solve problems that previous LLMs were not capable. That's because now we can generate much better high quality data at a fraction of the cost. Previously, you needed PhD or high-skilled people writing this data. Now you can use LLMs. Okay, so what is one of the biggest reasons behind this progress that we have seen in the past years? And as you can see in this plot, this is what Google Alphabet is spending in compute. Compute is growing a lot, okay? And we can also see OpenAI funding, cumulative funding over time. And notice that this is a logarithmic scale. Okay? So far, OpenAI has raised $180 billion. Okay? To put that into perspective, Navarra's PIB is 20,000 billions. So with that money, you could make all the people of Navarra work for 7 or 8 years. So it's a huge amount of money, and it is increasing over time, and that is what is driving this accelerated improvement. These AI labs have more and more compute every year, and that helps a lot to make these models more and more capable. And this is a very simple prediction. Any domain that is verifiable is going to be disrupted in the short term. As we have seen, they already have the recipe. They have the tool, they have reinforcement learning, they have all the money in the world. So they are going to expand the capabilities of these models to any area that is reachable. Okay, and to finish this state-of-the-art section, let me tell you a little bit about the open source ARC-AGI challenge, because as Michael has said, there have been many competitions in Kaggle about the ARC-AGI dataset, and people there compete using very limited resources, and that has forced them to try alternatives directions to the main labs, because when you submit a model for the ARC challenge, you only have 12 hours in a limited compute machine, so you cannot run there GPT-5 or those models. You need to go with much smaller models, and you need to try other ideas if you want to do well. And what is the learning from the open source competition? The main learning is continual learning. Okay, you can see in the bottom the numbers. If you train a model on ARC-AGI data and you make predictions with that model will score around 10%. Okay, but if you keep training the model on the new data, the model can jump up to 55%. So there is a huge jump just by doing continual learning. When you do continual learning, the model, when the data is novel enough compared to the training data, it can adapt to it, and this unlocks a lot of capabilities that, when we use frozen models, are not available. Okay, and this is not yet on the big AI labs. There are startups working on continual learning, but this is an unsolved problem, and here we see clear evidence that if we want to have systems that adapt to the novelty, continual learning is a very, very good tool. Okay, and this is something that I believe is useful, interesting. There is a blog post by Richard Sutton, one of the pioneers of reinforcement learning. It's called the Bitter Lesson, and the summary is that if you want to do work that will last, you probably should focus on methods that scale with computation. And there are only two main methods that do that, that are search and learning. And we can see that on ARC, okay? Very clearly on the continual learning. Continual learning allows to unlock new capabilities, and on search, because reasoning models, what they are doing is search. In those thinking tokens, they are searching for the answer to our question. So they can try different strategies, and because they have this notion of correctness, they can notice when the solution is correct, stop thinking, and return the answer. So both search and learn allow to adapt to novelty. Those are the two main components that will be needed for AGI. Okay, any question? No? So let's go to the finish of the talk. Okay, have we reached AGI? No, we have not. And ARC-AGI free is a clear evidence for that. If you have not played to ARC-AGI free, I recommend you to go to the ArcPrize website. You can play the games online. They are very, very funny. This is also an intelligent test, and it is based on the same philosophy of the previous versions of ARC. You only need very small prior knowledge to do this. The novel thing of this test is that all the games are new. Okay, ARC-AGI Foundation is now a game developing studio, and they are creating new games that no one has seen, and with novel mechanics, novel environments. So they make games that are new. So when you start a game, you don't really know what you have to do, and you learn to play the game by playing. There are no rules. You have to discover how you play the game. Okay. So if you have not played, after this talk, please go and check it. And ARC-AGI free is very, very interesting because it allows to show what is the current gap between humans and AI. Okay, so here in this plot we have on the x-axis how many actions were needed to solve the game, and on the y-axis you can see how many levels were solved by a human or by an agent. You can see here at the left there are many, many lines. These are all humans playing the game. The fastest human is the blue line. Then you have the best first run, because when you play the game on a second time, you already know how to play it, so you can solve it faster. Okay? And on white, I believe we have the average human play. Where is AI? AI is that green line in the bottom. So clearly there is something that current AI is missing. And ARC-AGI free is very, very interesting because since they are games, it is an interactive environment, we can measure how many steps are needed, because on the previous versions of ARC, you always have a fixed number of samples. You will have 3, 4, 5 for each task. So you could not measure how efficient was the system. If it needed 1 or 2, we didn't know. But now this allows to characterize very, very well how efficient the systems are. And this is in reality intelligence. As I said earlier, intelligence is a skill acquisition efficiency. So these games are new. When you start a game, you don't know how to play. And if you are able to beat the game very fast with a smaller number of actions, that means that probably you are intelligent. Or at least if we gave the same game to all the people in the room, we could make a rank that could be some kind of intelligence rank. Okay? Okay. So as you can see, the gap currently is huge. Humans learn very fast. AI is almost not learning. Okay, to understand why this is happening, let's go back and try to think what are the characteristics of deep learning, how deep learning works. Okay? So deep learning is a differentiable parametric function. In essence, deep learning is curve fitting. Okay? We have a model with some parameters, and we are going to fit the model to our data. To learn, we use stochastic gradient descent, and we have to define some loss function to drive the learning. And what is the challenge of deep learning? The challenge of deep learning is data. If we want our deep learning model to work well, we need to train it on a lot of data. We need what we call a dense sampling of the problem that we want to solve. If we don't have that, deep learning is not going to work well. So with LLMs, we have the luck that over the years, internet has grown into an enormous data set, and we can train LLMs on that, but that is not the case for many problems out there. So that is a very, very big problem for deep learning. So this is from my opinion, what are the fundamental problems of deep learning? First is data inefficient, I have already said. We need all the data of the world to train a language model. So that is a clear problem of deep learning. Humans do not need so much data to learn. Second problem, deep learning does interpolation. Deep learning is curve fitting. We are fitting some curve in our problem, and it is able to do interpolation. If you give a new point in that space that is surrounded by training data, probably it will give a good output. But when you start using data that is out of the training domain, results clearly worsen. And probably you have, if you have trained models, probably you have seen this. In domain and out of domain is something very, very common in deep learning. And finally, catastrophic forgetting. If you train a model on some data and you take that model and train on new tasks, the model will learn, but at the cost of forgetting what it has already learned. So these three are big problems that deep learning has probably at the root, and without very big changes, I don't think we can solve them. Okay, in the other side, we have another area of machine learning, that is program synthesis, where given some data, instead of fitting a model like in deep learning, we are going to generate a program that is able to generate that data. Okay, so let's do the same. What is the model of program synthesis? Well, it is a graph of different operators. We define a domain-specific language with some functions, and program synthesis is able to find what is the combination of those functions that is able to model our problem. Okay, how do we learn? Simply, we do combinatorial search. Okay, we can search that space of graph operators to find what is the program. The feedback is simply correctness. If the program outputs match the input and output pairs. And what is the problem of program synthesis? Is combinatorial explosion. Okay, if we have a very small domain-specific language, only a few functions, the search space will be small. But for real problems, we need many operators. Solutions tend to be many steps, and that makes the search space very, very, very large. And that is the main challenge of program synthesis. So a very, very simple of program synthesis. Here on the left, we have input-output pairs. And on the right, we have a possible solution. So this is something that program synthesis could have done. Okay, given input-output pairs, write a program that is able to solve the data. And this is a very, very important question. Why program synthesis is able to generalize from few samples compared to deep learning? So the answer is what is called the minimum description length principle. And this says that the shortest description of the data is usually the best model. It's very similar to the Occam's razor. So the simplest explanation for a problem is usually the correct explanation. And when we do program synthesis, we can find the shortest possible program that solves a problem. That is why it is able to generalize for a few samples. While when we use deep learning, we start from a model with a fixed number of parameters, and this principle does not apply on deep learning. So we can see that we have two very different methods. I like this analogy. Deep learning is like Play-Doh, like plastilina in Spanish. We start with some blob of Play-Doh, and we gradually shape it to fit our training data. On the other hand, program synthesis can be seen as Lego. We already have some pieces, different pieces, and we have to find how to combine them to solve the problem. And just a quick recap, we have already seen this. So we can see that we have two methods that are very, very different with different challenges. Deep learning needs a lot of data. Program synthesis does not need a lot of data, but suffers from combinatorial exclusion. So one idea that is being explored at Ndea, where I work, is try to combine both methods. You can use deep learning to guide the program synthesis process. It's very similar to the idea that Nalia showed 2 weeks ago with Go, where you have a search space that is huge, but if you use deep learning, you can train a model with intuition to guide the search. So we are trying to do something similar, but instead of playing Go, we are researching in program synthesis and combining it with deep learning. That's all. Thanks.
It's time for questions. Before that, I have forgot to say that Guillermo participated also on the creation of the master degree. It was a commission for that, so we are here also. So now it's time for questions. Questions, people?
So you mentioned that there's the incorporation and also the excorporation.
Yes.
Does it exist like a trade-off between these two paradigms? Let's say, I mean, let's suppose that we create a general intelligence, no? And we let it compete against AlphaGo in the Go bit. Do we expect the general intelligence to be as good as the AlphaGo or not?
That's a good question. I'm not sure how to answer it. I will say that there could be two ways to answer that question. For example, humans are much more general than AlphaGo, but cannot play at that level of AlphaGo. Even if we currently have it and we can learn Go playing against it. So, having that in mind, can we expect that another AI that is general could beat AlphaGo? Maybe, but I believe it will be unlikely. But what I believe it could do is the same as humans. It could learn how AlphaGo is and design a method, BetaGo or something like that, that might be able to beat AlphaGo. I believe that is more likely that a general method being able to beat some very, very specialized method.
How can a model keep learning after training and post-training style? When we saw a new problem, a new game, a new model exercise, how can it learn if the learning phases have already stopped and it will know its learn ways?
Yeah, it depends on the kind of model. I can tell you how this was done on ARC-AGI, for example. So if we go back to the ARC-AGI samples, back at the beginning, many slides here. Okay, so imagine that your model has been trained on other tasks, and now we ask the model to solve this task. Okay, so for this task, we don't know the output of the last example, but we know the outputs for the other examples. So we can use that information to train the model. For example, the idea is very simple. Let's imagine that this example does not exist and that this is the test example. So we are going to give the model these two examples as context, and we are going to ask the model to predict this output. And we have the label for this output, so we can train the model using supervised learning, using one less example from the task. This is one way. In a more general case, you could imagine that you have a more general system with some kind of world model, and for training our model, you don't need labels. You just need to interact with the environment, and you can use that data to keep training the model and learn new things.
How are those hormone scenarios being incorporated into the model?
That's a good question. There could be two ways, I believe. First one will be in the domain-specific language. You could craft some language that encodes this prior knowledge. You could add a function to change color, a function to rotate the object, to flip. That is surely one way to inject prior knowledge. The other one could be in the model that guides the search. That model will receive as input, for example, this ARC-AGI task. And if you train that model, it will hopefully learn those priors from the data. Yes.
This is like about the intelligence. Because you have a person, for example, you have system one that in 2 hours can learn and can have a 70% accuracy in sometimes. But maybe you can have system two that in 2 hours learns 30%. But if you give it 10 hours, gets 90%. It's slower, but it can be the first system. So which one is going to
I don't know. I don't know. It depends on what is your criteria. If you want to make an unbiased comparison, you have to fix the time for the two systems. Otherwise, you have these kind of contradictions. So it depends on how. If your test is 2 hours, system one is more intelligent. If the test is 10 hours, the second system.
So, we are programming, but the researchers are the ones that fix the questions for the applications for the integrated one. Like, what is the logic behind defining what that intelligence is relatively in these games? I don't know if it's clear, like, if we're the ones that really define what intelligence is, then that's what the models are going to do all that do.
I'm not sure if I fully understand your question. So this is one test of intelligence, but you could define any other test, and in reality, anyone is welcome to, if you wish, you could go this afternoon and create your own intelligent test. So the thing that matters is that you follow these principles of taking into account the prior knowledge, the training data, and the generalization capability, and that the test set needs to be private. If you create your intelligent test, you should not talk about it with anybody, because otherwise there is a risk of other people cheating. So maybe you were questioning, and I will agree with that this is just an implementation of a test. So it is possible that you could solve ARC-AGI 3 or ARC-AGI 2 or 1 with a system that is not general enough, because you have only focused on this problem, and that is possible. So how can we avoid that? I believe the answer is simple. If we are the people developing those systems, we have to see this test just as a tool. And we have to design our system to be general enough, not with the goal of being the first on ARC-AGI. That's not the goal. This is a tool to guide research, to make people ask the right questions. But that is the responsibility of everybody. It could be the case that, I don't know, Anthropic or OpenAI just want to be the first company beating ARC-AGI 3, and they take all the money they have and they start writing a lot of games. They create millions, thousands of millions of games and train a model just to play novel games, and they are able to solve ARC-AGI free. Okay, you will have a lot of publicity, but you have not made real progress to AGI, because what you have done is create a lot of data and train a deep learning model on that. It's a solution, but it's not a good solution for the problem.
Do you think how will we know if we eventually reach AGI? Because as you said, it really depends on how we present the test. Do you think it will be like a cycle of testing, or do you think it will be a one that is okay?
Yeah. My answer will be the same that ARC-AGI Foundation gives. So the goal of ARC-AGI Foundation is to make the gaps between AI and human intelligence visible. Okay, so ARC-AGI free shows this gap very clearly. If we are able to do progress in AI, it will become more difficult to create this kind of intelligent test. So there will be some time where you cannot find some test that it is easy for humans and difficult for AI. That is the goal of the ARC Foundation, to create tests that are easy for humans, difficult for AI. When that is no longer possible, we could probably say that we have reached AGI.
I have one question about the introduction. Because we were talking about the typical problem that plays tests. So you really the optimal.
Yes.
And might be on the examining problem. That even if the model is performing more optimal, it's only designed for that task that is playing tests in the most optimal way. 100% that model you will consider it better than another one that performs worse but with a higher reasoning behind it.
I will not say that the reasoning behind it is the important factor. The important factor is that if you take that system and apply to another task, it is not able to adapt. It's just a table. So intelligence is that capability of giving a new task, being able to learn quickly and solve it quickly. A table does not have any adaptation capability. It's just a list of numbers. So it's probably the most dumb thing the most dumb system that we can think of. Although it could be very, very capable, depending on the problem. For some problems, it's the best tool that we can design, but it does not have any adaptation capability.
Why too much investment? Or why do you think, what do you think that is the final purpose of a general intelligence?
Well, I believe the investment is behind a belief that AGI will be reached soon, maybe next year. Really, nobody knows when it will be reached. Maybe it's 20 years. We don't know. We don't know. But investors are betting that OpenAI or Anthropic are going to create at least very capable models, and those models will be used in all economic areas, and that will create a lot of value. That's the bet that they are doing. We don't really know if the bet is correct or not yet. We will know, I don't know, 5 years or something like that. We will see if this was the biggest bubble of all times, or if it was the right bet. Yeah.
Years ago, when API was starting to be a topic, one of the main points about it was also consciousness and self-consciousness. And I want to know if it's still something that is being tested or trying to set, or if we are now separating self-awareness and consciousness from AGI.
I'm not really an expert on that topic. From my point of view, consciousness and intelligence are orthogonal things. So you could be conscious but very dumb, and you could be there could be a very, very intelligent system that has no conscious. So far, well, some people believe Claude is conscious, but most of the people agree that it's just a machine, and it has some degree of intelligence. It is capable of solving novel problems. Of course, it is not at the level of AI, but it has these systems have some intelligence. So my belief is that they are orthogonal things, but I believe that's something that is not known.
What do you expect to achieve AI?
I don't know.
To make a prediction?
No, I believe those kind of predictions are worthless because you mentioned we have a podcast. Yesterday we were talking about the Dartmouth conference back in 1955. And that conference is famous because the term artificial intelligence is believed to be coined there. And it is funny because in that conference they believe that in 2 months, in one summer, they were going to do a lot of progress on AI. So if we look at with perspective, and they were very, very brilliant people, the most brilliant people at that time had that belief. What can I say today that when we are going to find AI? I don't know.
The public talking about the virtuous cycle.
Yes.
Like training models. When do you think? I mean, do you think it will have a point where it finishes, or we can like do that until when?
Yes, like a self-improving cycle. I don't know. The thing is that how the big labs train these models is very secret. We know the recipe because there is open source AI, but each lab has its own tricks to curate the data. That is very, very important. I don't know, but my intuition is that probably deep learning alone is not enough to ignite that kind of, or at least deep learning as we know it today, is not enough to ignite that kind of self-improving cycle.
And then do you think you have spoken about extrapolation, the problem of extrapolation?
Yes.
Do you think that reasoning can help you doing that extrapolation?
Yeah, of course. Reasoning allows the model to have some degree of adaptation to new domains. But I'm not sure if that is enough to solve this fundamental problem of deep learning within the current paradigm. If you allow the models to keep learning with continual learning, maybe that with reasoning could be enough to have a strong system, but I don't really know. I'm not sure if it has been tested. The thing is that these models are so huge that continual learning on them is also a big engineering challenge.
maybe more philosophical. There is Choel, no? People speaking about the tradition and so. And also there is Jan LeCun there, which also has the view that LLMs are not enough for AGI.
Yes.
Can you, I don't know if you know, can you compare the approaches? I mean, are they in the same line, or do they have different approaches for this API?
I don't think they are the same approaches because I haven't read Jan LeCun talking about program synthesis, and Francois is one of the most, I don't know how to say it, one of the people that is clearly in that camp. I will have to research more about it. I am familiar with some of the latest talks by Jan LeCun, but he has founded a company very recently. I don't remember the name. Something like machine intelligence or something like that. And I believe he's mainly focused on world models. So I don't really know how different is his approach compared to the state of the art. Personally, I like the ideas from Jan LeCun a lot. He has some very cool papers, and he's very contrarian to the current line of thought of the field. So I am curious to see what they are doing.
Yeah, one more. So if I don't know if in Ndea you are working also on the ARC-AGI benchmark or not, but if you are able to beat this or pass this benchmark, could it be like if Francois is the author of the ARC-AGI, no? If he has access to the test, what would be the opinion from outside?
Yeah, of course. That also will happen to me. For example, if I'm not sure if I'm going to participate in ARC-AGI 3, or probably I will try something. I don't have yet an interesting idea to try, but if I participate, I will have to do it some kind of open source submission where everybody is able to see my work, because otherwise the people will say that I have cheated. Although I don't have access to these datasets. Ndea and the ARC-AGI foundations are separate entities. Of course, there is relation because Francois and Mike Canup are in both sides, but workers do not have access to any data. Yeah, I don't believe. Well, if we wanted to make some claim, some public claim about solving ARC-AGI 1 with a new approach, I will argue that probably we should open source the system so everybody can see it and check that we have not cheated, because otherwise, it will be the same as you make the exam for your classes and you say, okay, look, I have a 10 on my own exam. So yeah. Thank you.